Okay. Video number 2 of the day. I don't think you'll have this many videos for the modules that I have. And if you do, they won't all be of me. I know you're gonna get sick of me so fast. Um, so I want to do lecture videos because it seemed to help the students in my last online asynchronous class. And I know a lot of instructors don't do these videos, but I just think that it gives a sort of personal touch to the class for me. And then that way you really have a better understanding of what I want you guys to know. But if I have multiple videos, it won't just be of me. I think I'll try to do one video per topic and then other videos from other experts coming in and talking. Okay, so not just me. This module, again, is going to be unique because we had the welcome video with me and Henry, and she's still here. She's still mad at me. And this one. This is officially module 1. Yay. Where we start to talk about the text. And this one's going to be welcome, Henry. Okay. Relatively straightforward. We're going to talk about some science and methods and principles of science. And then I'm going to dive a little bit into matter, energy, and life. Henry Gyrone, do not jump on that bookshelf. Um, and it's sort of an introduction into some of the chemistry and biology. And I think it's really important to have this intro because we're going to dive further into some of this later on in the class. And I'll tell you why it's important as we go. So let's share my screen. Share. This. And I want this. Henry Guy rounded on jump up there. She's being so naughty today. I know she's hungry, but okay. Module 1, the principles of science, matter, energy, and life. So the first thing we're going to talk about is the most important concept with science and why it is such a relatively straightforward thing. It's because we all scientists follow the scientific method. It is the most integral part of science and understanding how science works and how to build a scientific experiment. So we have the scientific method. You've probably heard this phrase before, but we're going to break it down. And then this is going to be what your homework focuses on. And I do want to make it clear, I'm going to talk about your homework at the end of this slideshow because it's all going to pertain to the scientific method. You're going to ask a question, make an observation, ask a question, and build a hypothesis. I'm going to show you how you're going to do that. So the scientific method, observation. Let's move my face and Henry's face probably. I don't know how to move it. There you go. So making an observation. It's as simple as taking a look outside. Science began with a bunch of these dudes looking around and making an observation, like watching an apple fall from a tree. Smelling the garbage that gets stinky after a few days. Why does it get stinky? I guess that's jumping into questions. So smelling the garbage, that is an observation. Tasting the change of grapes over the course of different years that make differently flavored wines. I lived in the Willamette Valley for a minute. Also, I love wine. And I had a lot of people talk to me about the science behind growing these grapes. And they observed that some of these grapes, which were the same type of grapes, changed their flavor over the course of a few different years. I keep moving my face. And in this particular case, I had this idea because the leaves are changing right now. Seeing the leaves change on a tree over the course of a year. Change color, change shape, change the fact that they're even there. That is all making an observation. I'm looking outside and I'm like, oh, those trees are starting to turn red and yellow and orange. Interesting. So here's the idea of these trees changing in deciduous trees. In spring, they're bright and green, and in summer, they might start to wilt a little bit, but they're still pretty green. But by autumn, they're starting to turn these beautiful colors. And then in winter, they're gone. So making that observation of, oh, there's a cyclical response to the year and these leaves changing. That is an observation. And then we ask a question regarding that observation. And these form naturally, right? I already started asking questions in the last slide because that's a natural response to these observations about the how, the why, the when, the etc. So why do trees change color over the course of a season? What is happening to the tree as it's changing colors? What factors lead to the loss and gain of leaves over the season? Does the cycle occur at the same time every year? So I bolded that one because that's the one we're going to look at because it was the simplest one to walk through. Does the cycle of these leaves changing occur at the same time every year? So this was probably one of the first questions that man had without even realizing that he was following the scientific method. Does it happen every time or at the same time every year? So then you build a hypothesis and you form this hypothesis. Okay, I was like, do I define it? I want to make sure I do. So then what we do is we make these inferences about the questions that we have asked based on what we might already know. And the Oxford definition of a hypothesis is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation, which is just a really fancy way of saying we might have some inferences about the question. Like we might have some ideas as to how we would answer this question based on what we already know. So in this case, my hypothesis is, yeah, the cycle occurs at the same time every year. And then if you can, and sometimes this might not be feasible, or maybe you're like, well, I'm just making a good guess here. The cycle occurs at the same time every year because, and I added that because there, of environmental factors like weather and temperature. So that's my hypothesis. The bolded one, I think, is the more accurate. That's all I'm looking for, is the cycle occurs at the same time every year. You don't have to have a because, but a lot of cases you do. In this case, I'm not gonna do the because. I'm not gonna do the because. So after you build this hypothesis and you write this hypothesis, you then experiment. You make an experiment. You have to design this experiment to test your hypothesis, to help answer this question. So perhaps with the hypothesis of, yes, this happens every year, you would set up a procedure. Step 1, I would choose 10 trees of variable species to watch over the course of the year. Step 2, record the date as soon as each tree loses 5 leaves. Step 3, record the date as soon as each tree has 5 leaves back grown on it. So what we're doing is step 2 here is recording the date as soon as each tree loses 5 leaves in the fall, right? When leaves start to change. And then my step 3 is after we record those dates, we're going to wait and then we're going to record the date on each tree, the same trees, as soon as those trees begin to grow 5 leaves. It's a simple procedure. So that is my hypothesis. Oops. I see. Okay. Sorry, I'm looking to make sure I'm going in the right direction. So that's like the easiest procedure to set up this hypothesis. This is the experiment, essentially. And right now the experiment is simply visual and recording. And it's to collect that data. We want all the data. And maybe we'd want more than 10 trees. 10 was just an easy number I picked out of the top of my head. We certainly want more than one, right? We need to have variables, which is the next slide. So what is a variable in an experiment? It is an object, an event, an idea, a feeling, a time period, or any type of category that you are trying to measure. So it's effectively what you're trying to measure within this experiment. The dependent variable is the variable that depends on other factors. So in this case, in this experiment, the variable that we have, the dependent variable, is the changing of the leaves that depends on the time of year. That's our dependent variable, is the changing of the leaves and the falling of the leaves. The independent variable is the variable that stands alone and it isn't changed by other variables. So the time of the year does not depend on anything in this experiment. It's going to happen. It's going to happen on its own. It does its own thing, and it has no effect. It's not affected by anything else. The time of year is going to happen. So that is independent. That is our independent variable. And then our control is used in an experiment to acquire baseline data. This baseline data can be compared to the experimental data to see the relative effect, if any, on the independent variable on the dependent variable. Whew, that is a mouthful. And I was really trying to think of a control for this experiment. And because it's environmental, it's not in a lab, it was really hard for me to think of one. So the best Um, uh, oh my gosh, my words are hard today. The best option I came up with was a placebo, which is a control in medicine. So I don't know if any of you have, I don't know, I watch a lot of Grey's Anatomy, but a placebo effectively in medicine is there will be a trial run if they're testing a new medication, right? If they're testing a cancer drug, and they'll set up this drug. It's called a blind test, where the patient is like, yeah, I know I'm in a test, I'm in an experiment right now. And they're either given cancer medicine, the cancer medicine that they need, or they're given a placebo. They don't know what they're given. And the placebo is the control, because if these patients that have the placebo are changing as at the same rate that these cancer patients who receive the cancer drug are changing, they realize, oh, the cancer drug's not actually working. Because we have this control where we can see somebody who thinks they're taking the medicine, but it's not doing anything, versus the people who are taking the cancer medicine, and they have the same data with both of those groups of people. Versus if the placebo, it's the person doing the placebo and the cancer isn't changing, nothing's happening, but the people who are taking the experimental drug, if the cancer starts to go down, they say, oh, the placebo or the cancer medication is working. We have this control that shows these people who think they're taking the medication, so we know it's not psychological. It's not working on them, but it is working on the cancer patient. So that's the control variable, the controlled variable within an experiment. And if it doesn't make any sense, I'm happy to walk you through that again. But there needs to usually be a control in a lab experiment, and a dependent and an independent variable. So those are what variables are in an experiment, right? So then you have the experiment, you've set up the experiment, and you've collected all this data over the course of a year. What does all your data mean? So perhaps we found that all of the leaves fall between September 1st and October 15th, and the leaves all grow back between April 10th to May 15th. This could end the experiment. That's our data. That's what we have. Okay, cool. Let's send this out into the public and say, this is when leaves are going to lose their leaves. Sorry, trees are going to lose their leaves. And this is when it all grows back. Also, I pulled these dates out of my butt. I don't know that this is true. I did not run this experiment. Or you could start a new one by going back up to observation. You say, wow, that's weird that there's this 45-day window that they're losing the leaves. Let's ask a question. Why this window? What is happening in this window that's causing these plants to lose their leaves and grow them back? So what factors cause all the leaves to fall between September 1st and October 15th and grow back between April 10th and May? So we can start over and say, let's do another experiment. Let's run another test. Let's run another ask another question, build another hypothesis, experiment, and then come back to analysis. So once you've maybe done that, you're going to build this conclusion and conclude that entire process. And this is just compiling all the information that we've collected into a database, or writing up a nice summary. We write a 100-page thesis, which I just did. It sucked. You write a 500-page dissertation if you're getting a PhD. And then you can publish it so that other scientists can review your data and interpret it with their data sets, and then continue our research. So that is the scientific method. It's these 6 simple steps. It can be as simple as seeing an observation outside, asking that question, forming a hypothesis. And then you do have to do the experiment, and it's something you can do at home. You probably do the scientific method on a regular basis. Then you analysis, then you analyze it, and then you conclude. Our scientific method. So that is the first and foremost most important part of science, is the scientific method. And this is what you're going to do your first homework on. Again, we're going to talk about that at the end of this slideshow. But I want to dive into the next part. So for this class, or for this module, I had you read 2 chapters, I think 3 and 4, if I'm correctly remembering. So the first one was just the principles of science. And this is the biggest principle of science. It's asking a question, building hypothesis, and an experiment. So this is what I wanted you to take out of chapter 3. The second part was matter, energy, and life. And again, this is just the foundation of what we're going to talk about for the rest of the course: matter, energy, and life. So all life is made up of matter. What is matter? It is something that occupies space and has mass. We are matter. Ha, we matter. We do. We matter. And we are matter. Henry's matter. She's being a very dramatic matter right now. She's laying on the floor. All matter is composed of elements, which are substances that cannot be broken down or transformed chemically into other substances. And each element is made up of atoms, each with a constant number of protons and unique properties. So we're going to dive a little into chemistry. Full disclosure, I am a chemist. That's my focus. It's my primary love of life. So I got really excited about this, but I didn't want to dive too hard into it. I mean, I did, but I won't. Here is an atom. If you have never seen an atom before, it is composed of 3 elements. What do I have here? So we'll talk about those elements in the next slide. So all of the elements listed on the periodic table, which I will show you here in a second, are made up of atoms. And it's the smallest particle of an element that retains the characteristics of that element. So an atom is the smallest thing, one of the smallest things we've found. They found smaller things, but we don't have to dive into that. They're very small. An atom is very small. A proton, so again, it's composed of 3 things. A proton is the positively charged portion of the nucleus. So in this case, we have 2. This is a helium atom. So this has 2 protons. And the protons are always in the nucleus or the center portion of the atom. So these 4 items are the nucleus, make up the nucleus. And the bottom here, these plus size charges are our protons, positive protons. That's how I remember it. A neutron is part of the nucleus as well. And these are neutrally charged. So they have no charge. They're not positive. They're not negative. They're just hanging out. They add to the mass of this atom, but they don't have a charge. And that's important. So it's neutrally charged. And then finally, the electrons, they orbit the nucleus and they are negatively charged. And what we're seeing here is we're seeing 2 electrons and 2 protons. So this atom as a whole right now is neutrally charged because you have 2 negative charges balancing out 2 positive. So think about it in terms of math. If you love math, -2 plus a +2 is going to equal 0, right? That means it is neutral. And that's how these atoms want to be. They want to be neutral because if they're positive or they're negative, they tend to, that takes a lot of energy, and they want to be neutral. They want 0. So they're finding other atoms to balance out with to make neutral scenarios, which we don't have to dive into. That's not important. But just note, they want to be neutral. Okay? So proton positive. Neutrons neutral. It's easy enough. And then electrons are negative. Here's the periodic table of the elements. I highlighted the important ones. I guess I didn't. So I guess I liked this one because it pointed out the atomic number. So we starts at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the atomic number is the number of protons present in the atom. And that's important. The number of protons will never change in an atom. And if it does, it means it's a different element. So hydrogen will always only have 1 proton. Helium will only ever have 2 protons. That's why I was like, oh, this has to be helium because there's 2 protons here. Lithium will only ever have 3, etc. The symbol represents the name of the element, and it was just something to smallify those names. So hydrogen is H, helium is He. I do want you to know at least 4 of these. And the ones I want you to note are carbon, which are C, because we're going to talk about carbon a lot in this class. Oxygen, which is O. Chloride, which is down here. Chlorine, which is Cl. And then the funky one I want you to note is 11, which is the same one up here. This is Na. This is sodium. And this is a funky one. I don't remember why they gave it an Na. It has to do with Latin, something in its Latin roots. But so sodium is Na. So those are the four that are going to be really important. I think I'll probably show other ones in the class too, but I'll make sure to note that. But carbon, oxygen, chlorine, and sodium are going to be the four most important, at least in the time being. Okay. So carbon, again, is one of the most important elements in the world. It's one of the most important biological elements. And that's because carbon is what makes up most of life. So carbon atoms bonded to other carbon atoms or other elements form the fundamental components of many, if not the most, molecules found uniquely in living things. And some of these molecules made up of carbon are lipids, proteins, enzymes, nucleic acids. I don't expect you to know these or remember these, but what I do want you to note from this slide is carbon is one of the fundamental elements that make up life. We are made of carbon. Trees are made straight from carbon. And the reason that is, again, I don't need you to remember this, but it's because they have four bonding. I know. They have four bonding valence electrons. And what that means is they bond with just about anything. And once they've bonded, they're very, very stable. So that's why carbon is so pertinent and integral to life. They bond primarily with hydrogen. So down here, I'm sorry, these are so small, you can barely see them. And again, I don't need you to note these, but this is an organic compound. This is a fatty acid. It's fatty acid because it has an OH member on the end. Carbon bonds with hydrogen really nicely and forms what we call hydrocarbons, weird, which make up the fundamental foundation of life. You got your unsaturated fatty acid. You got your steroids. I don't even know what this word is, to be honest. I work primarily with lipids in my thesis, which is a straight carbon and hydrogen chain. Doesn't matter. You don't need to know that. But what I do want you to know, carbon is integral for life. We need carbon for life. Okay, let's jump. Hold on. How do I? Okay, I'm back. Sorry, honestly, I just really had to pee. I drank like 5 cups of coffee this morning. Henry, calm down. To reiterate all of this, I wanted to go over some chemistry with you because we are going to talk chemistry in this class at its simplest form, so don't panic. But chemistry is so important in environmental science, especially regarding climate change and human emissions, right? So I wanted to sort of start talking about chemistry in this capacity at its simplest form, particularly with carbon. But we're also going to do some thermodynamics, woo, which is energy. So ultimately, most life forms get their energy from the sun. We need energy to survive. And energy takes on different forms. Plants use photosynthesis for their energy. It captures sunlight, and then herbivores will eat the plants to obtain that energy. Our energy comes from food, right? I don't know if you've heard, how many calories is this chocolate bar? A calorie is a form of energy, and we need that energy to survive. So calories are super important for our life, our ability to evolve and to thrive. So herbivores will eat the plants that have photosynthesized to obtain energy, and then carnivores eat the herbivores. And eventually decomposition of plant and animal material contributes to the nutrient pool. It's the circle of life. Look at it's like Simba. It's the circle. She's so mad at me right now. I know. Oh, my sweet, sweet baby. Come on. And I found this really, I don't remember if your book had this or if I found this online, but I really liked the idea of the energy primarily comes from the sun, right? And that energy is in the form of heat. We get these plants that use that heat and that energy, which is then consumed by animals or decomposers by fungi, bacteria, and worms, and then turns back into heat. And decomposing material, which is about to happen in the fall here, after the leaves fall and begin to decompose, they produce heat. It might not be as much as like the sun does in the summer, but it does produce a small amount of heat. Matter is relevant to a particular case of energy transfer called a system. And everything outside of that matter is called the surroundings. I'm sorry, this is not the best picture because it's super blurry, but I liked what they had here. This was not in your textbook. So you have three different types of systems. You have your open system. And an open system is like a pot of boiling water. You have heat entering that system. And you have this pot of this water that is boiling, turning into steam and leaving that system. And it's also releasing heat. So you have heat entering the system, heat removing from that, leaving that system. And you also have matter in the form of water. And that water is in that system, it's part of that open system, and is also leaving that system. Okay? That is an open system. You have a closed system. So this is essentially, you put a lid on that pot of boiling water. And when you do that, the steam cannot leave that system. The matter cannot leave that system, in a sense. But the heat is still leaving that system. You have heat entering that system from the burner, and you have that matter, or sorry, that energy leaving the system. So there is still heat being released from the lid. But the matter itself is not being released from that system. And then finally, you have an isolated system. And this is like a thermos, a really nice heat trapped thermos, where you put hot water inside for hot cocoa or for coffee or whatever. And then you put the lid on. Heat cannot escape that. That's why that beverage stays warm for so long. Heat cannot escape it. And also the steam that is in that system cannot be released. So you don't have matter and you don't have energy either coming into that system or being released in that system. That is an isolated system. So thermodynamics, just dive in a little. Nobody panic, please. Because I do want to talk about the first law of thermodynamics. And it states that the total amount of energy within the universe is constant and conserved. So there will always be the same amount of energy in the universe. But that energy can be transferred in different ways. But you're not going to add energy out of nowhere or remove energy out of nowhere. That defies the law of thermodynamics. So what we're saying is living organisms can obtain energy from their surroundings in forms that they can then transform into usable energy to do the work. So photosynthesis, they're taking on the energy from the sun, building it into food, but they will release that energy in other ways. The energy is not created and not destroyed. It remains constant. Okay, so that's our little baby tap into thermodynamics. It's just understanding the energy cannot be created and cannot be destroyed. We're going to look at cells now, briefly. I have 4 slides on that. And there's 2 types of cells. There's 2 categories. You have your prokaryotic cells. These are single-celled unicellular organisms that lack a nucleus or any other membrane-bound or organelle. And it's bacteria and archaea. So these are like the simplest form of cells. You have your eukaryotic cells. Oh God, everybody pronounces that one differently. And full disclosure, I actually have no idea how to pronounce it. Eukaryotic cells, pretty sure it's that. And these are the cells that form animal cells, plant cells, fungal cells. So these are a little bit more complicated. They have a lot more factors, as you can see here. No, I'm not going to have you memorize all of these. That's silly. I don't even know if I'll have my biology class memorize all of these. That's silly. There's so many. Just note that there is a nucleus within the cell. That's the most important part. And the mitochondrion, which is the powerhouse of the cell. Yeah, they don't have a mitochondrion. Ha! So that's the big difference between an animal or a eukaryotic cell and a prokaryotic cell. Prokaryotic is bacterial, and this forms us. This is what makes us up. Oh, was that all I have for that? Oh, it was. See, nothing crazy. Just note there are singular cells, unicellular, and then we have these cells that make up animal cells, plant cells, etc. And here, this obviously I stole this from Google. There's a screenshot. This is the biggest differences between prokaryotic and eukaryotic cells. No membrane-bound nucleus in the prokaryotic. Cell walls made of, I don't care about that. This is another one I thought was kind of important was they don't move. These ones don't necessarily move, but they do propulse. and they can adhere to things. So they stick to things, right? Versus eukaryotic cells have that nucleus. That's important. They might have cell walls made of cellulose. But these ones can move. They have flagella. That's a fun word, flagella. And then our prokaryotic are much smaller than our eukaryotic. Micrometers are very small. These are very, very small. And just to give you a sense of size, this isn't the best. This was the best I could find. Actually, this was in your textbook. This one's in your textbook. That's why it says support, because it's an online textbook. It's not to scale in terms of visually, not to scale. So it's kind of hard to wrap your brain around. But what it does show you here is you can see these items with your naked eye, 100 micrometers you can see with your naked eye. So not quite animal and plant cells, but you can see a human egg, a frog egg, chicken egg. Here's an adult female, ostrich egg. This is a logarithmic scale, which is why it's kind of hard to wrap your brain around. And then in a light microscope, which I have here, and I'm going to try to use it this term in this class. I got to figure out. So I have I have my very own microscope, and I love her. Her name's Cindy, and I really want to try to set up. I can put my phone. I have a device that I can hook my phone up to the microscope, and I'm hoping I can sync it somehow so I can do a video. It'd be so cool. So you guys can use a microscope, sort of. And then finally an electron microscope, and I don't have that. You need the tiniest, tiniest, tiniest microscope to see these itty bitty things, to see an atom. Although there was a award-winning photo a couple years ago. I'll probably have it on one of my slideshows because I think it's the coolest thing, where somebody finally got a picture of a strontium atom. So the smallest thing in the world, they got a picture of it. It's so cool. I think it's so cool. Okay. So that's just the visual idea of cells. And that is my slideshow on cells, or my portion of the slideshow on cells. So then going into that, we have plants. This is algae. We're going to talk a lot about algae this term in the issues of environmental science and algae. And then bacteria, this is cyanobacteria. And cyanobacteria is some of the first organisms that ever existed on Earth. And these are photoautotrophs that can carry out photosynthesis. Do I talk? Yeah, I do talk about it. So these organisms here rely on the sun to live. That's their form of energy. So photosynthesis there's two different types of trophs, essentially. So an autotroph is an organism that can produce its own food. That's these guys. These guys are autotrophs, specifically photoautotrophs, that produce their own food. And plants are photoautotrophs, a type of autotroph that uses sunlight and carbon from carbon dioxide to synthesize chemical energy into the form of carbohydrates, which is the energy they need to survive. We also need carbohydrates to live. If someone says, don't eat that bread, it's bad for you, they're lying. You need carbs to live. You need it. Eat the bread in a form of pizza. I don't care, but eat carbohydrates. All organisms carrying out photosynthesis require sunlight. They have to have that sunlight. The sunlight, so sunlight produces an energy level wavelength. I'm not going to require you to know this. And that wavelength is really, really important because it's that energy they need to survive. So it can't just be the light bulb. They need sunlight. And you've probably seen like, this is the worst, hey, stop it. It's the worst case of an example, but like a grow room, right? They use UV lights. It's the same, and they have to use UV lights because that UV light is that wavelength, the very specific wavelength, the same wavelength that comes from the sun. If we enter a nuclear apocalypse and we need to grow food, we'll have to find UV light to grow that food. That's the only type of wavelength they use for photosynthesis. Hopefully that won't happen, but prepping for the worst, I guess. Heterotrophs are organisms that are incapable of photosynthesis and that must therefore obtain energy and carbon from food by consuming other organisms. So even if that food organism is another animal, the food traces its origins back to autotrophs in the process of photosynthesis. So ultimately, even we get our energy from sunlight, in a way. Henry does too, although Henry really likes fish. That's her favorite. So that's how she gets her energy, is by eating a lot of cat food and getting mad when she's not getting that cat food. I know. And we are incapable of photosynthesis. I can't just sit out in the sun and be like, oh, I'm full. That was delicious. I have to get my energy and carbon from food. I eat a lot of chicken wings. That's my favorite. I love chicken wings. I have an air fryer. Listen, if you don't have an air fryer, I could sell an air fryer to a fish because they've changed my life. I literally air fry everything, and I air fry a lot of chicken wings. So that's what's for dinner tonight. I'm pretty stoked. But that's how I get my energy, is from food. I did put the photosynthesis chemical equation up here because I think it's important. And I probably will test you on this because I think that everybody should understand the chemical equation for photosynthesis. Photosynthesis is just the idea of sunlight hitting these leaves. They are taking it, so these trees, these organisms are taking in carbon dioxide with sunlight and water from the ground, and that's how they create their carbon. So there was this great video a while ago of this guy walking around like Ivy League colleges, and as these students were graduating, and he was like, can you answer the simplest question? What are trees made of? And they had no idea how to respond. And it's hard because you're like, I don't know, like a leaf, like a trunk, but what is that made of? Ultimately, it's made up of carbon. A tree is just straight carbon. And that's because they take in carbon dioxide with water, and then you have to have that sunlight. That is the factor that allows this chemical formula to take place that turns all of this into sugars and oxygen. And they respire oxygen, so they breathe out that oxygen, which is what we need, right? We're breathing in the oxygen, breathing out the carbon dioxide for them. So we have this symbiotic relationship with these trees where we're breathing out carbon dioxide, which then they consume with water to grow. So that's their food. This is their food. This is how they eat. And they build and they grow. And then using that sunlight, they build these sugars, which has a lot of carbon in it, and oxygen. So they respire the oxygen for us, and they make these sugars, which then build this tree, and the tree is made up entirely of carbon. And once that tree decomposes, it turns into carbon. So that is photosynthesis. I don't need you to remember all of these things. Again, I need you to know carbon. This is carbon. This is oxygen, right? Carbon dioxide has 2 oxygens. Don't worry about the 6 in front of it. Doesn't matter. It does, but not for the sake of this class. Hydrogen and oxygen form water. 2 hydrogens and 1 oxygen form water. This is H2O. The sugar I do not need you to know. C6H12O6. That's a sugar. And then oxygen. What I will test you on is, what does a tree consume? How does it consume that? And then what does it put out? And what I want you to say is, it consumes carbon dioxide and water using sunlight, turns to sugar and oxygen. That's what I would want you to know. And then respiration is literally just this equation backwards. So respiration is it respiring, I guess the best way, actually right now, is respiration is happening. It's dropping these leaves, which are decomposing. And as those leaves decompose, they respire carbon dioxide. That's what that means. And that's important because then I have this graph. We're going to talk briefly about graphs. So, want some more coffee that I should not be consuming right now, but it's delicious. Let's talk graphs. Here's a graph. Hopefully many of you have seen graphs before. If you have not seen a graph, or you don't really fully understand a graph, we're looking at what we call axes. So this line at the bottom, this is an x-axis. And this is usually our independent variable, is on the x-axis here. This vertical axis here, this is what we call a y-axis. And I remember that because a y has that tail on the bottom. So if you have a y, boop, boop, and that y would just lead down into this vertical axis. That's just a mnemonic that I use to remember y-axis. So this is our y-axis, and that is our dependent variable. So this material depends on the year, right? This axis. And what we're looking at is we usually start at like 0 at where the X and the Y axes meet at the bottom left-hand corner. This doesn't quite start at 0, but it would be 0 if we were to extrapolate the dates, which just means if we were to go to the very, very beginning of this number versus the very, very beginning of this number, we would have 0. So it starts here, which means we're going up as we go up the X or the Y axis, pardon me. So we're going from 320 to 400 on the Y axis. So this is increasing as we go up the Y axis. Similarly, we're increasing as we go over on the X axis. So we're starting in 1960. This graph is missing an element, one of the most important ones. It's missing a title. Titles aren't, so the y-axis has a title, which we'll talk about here in a second, but we're missing the title here. And I wanted to point this one out because it's the most obvious, or at least the clearest. We're looking at the year. So this is year. So we're looking at 1960 on the far left, and it's increasing to 2010 as we move to the right. So we're increasing as we go. So we increase in this direction and increase in this direction along each axis, right? Should say year on the bottom. You should always have titles on your axes. And then your your y-axis here has this title. So this title here says carbon dioxide concentration in ppmv. It should just say ppm for simplicity, I guess. What we're looking at is carbon dioxide concentration, 320, 340, 360. It's increasing, we know that, in parts per million. And all that means is that for every million particles, so if we just have a bunch of oxygen particles floating in the air and we can say this is a million particles of oxygen right in here in this little box, 320 of those million oxygen would be carbon dioxide here, if that makes sense. So that's what that's saying. Up here, every 400 of that oxygen, of that 1 million oxygen, so instead it would be, oh, I can't do the math. It would be 1 million minus 400, because that 400 would be the carbon dioxide. That's what that means, parts per million. Full disclosure, I actually have no idea what the V means, but I do know that we're looking at 320 to 380 parts per million. So this graph is showing us the atmospheric carbon dioxide from it's actually like 1956, I think, to 2011. And what we're seeing is this black line is the average, and it's rising, right? We're going from under 320 parts per million carbon dioxide all the way up to almost 400 parts per million carbon dioxide in 2011. This is huge. This is a big deal. This is a very famous graph in the world of environmental science and chemistry and climate science. This is called the Keeling curve, and it's measured by oh God, Charles Keeling? This is embarrassing. I should know it. I think it's Charles. So Charles Keeling, who has now passed away, is a famous atmospheric scientist. I actually had the opportunity to talk with and potentially go and work with his son, Ralph Keeling, who does work in carbon dioxide down in Scripps University down in San Diego. He's so nice, nicest guy I've ever met. But he works primarily with mathematical modeling of carbon dioxide. And I was like, no math for me. Thank you. I just like the chemistry part. Super nice guy, super smart guy. So his father, Charles Keeling, I think it's Charles, began this process. He went to Mauna Loa, Hawaii, and he did that because Mauna Loa is a very tall mountain. It's actually the tallest mountain in the world, not the highest, the tallest mountain in the world. If you look from bottom of the ocean to the top of the mountain, Mauna Loa is the tallest. And if you've ever been up to Mauna Loa in Hawaii, you're above the clouds, basically. You get very accurate readings of the Northern Hemisphere atmospheric quality. And so he wanted the best readings without a whole lot of human, I guess, interaction. So there are humans living in Hawaii, obviously, but like getting readings at Mauna Loa is going to be a lot more trustworthy in regards to like a mixed atmospheric reading versus like going to Seattle and trying to sit on Mount Rainier because you're going to get all of those carbon dioxide fumes and it's going to skew the data. So he went to Mauna Loa, which is out in the middle of the Pacific Ocean, to get these accurate readings of the Northern Hemisphere atmosphere. And so he's been taking, well, him and his son, Ralph, have now been taking these readings every single day. Oh my gosh, and he like did actual chemical laboratory work a few hours every single day to collect these very accurate readings of carbon dioxide concentrations in the atmosphere. So that's why this is so famous, because it's very accurate. And now we take satellite imagery, so we're not doing laboratory work every single day for these readings. But we're finding, and he found, that the carbon dioxide is rising in the atmosphere. And it's rising very, very quickly. We're going to talk about this more when we talk climate change. But what I wanted to point out, and the reason I put this graph here is if we zoom in on these cycles, we have this like sinusoidal sort of cyclical pattern where, okay, I'm almost done. Where in April and July, it rises. So the carbon dioxide rises up here and then it falls around October. Why is that? Why would that be happening annually every single year? And we get this cycle like this. And the reason that's happening, because globally, we have the fall happening in the northern hemisphere in October and January. That's weird that it's like this. It should be opposite, actually. So we should be seeing lower carbon dioxide readings, so less carbon dioxide in the spring. And the reason we would see less carbon dioxide in the spring, I'm saying this right. Yeah. I don't know why this is backwards. We would see less in the spring is because all of these plants are taking in carbon dioxide in the spring so they can grow their leaves. They need that carbon dioxide as part of the photosynthetic process, right? So they're taking in all this carbon dioxide in the spring to grow their plants. And they're also breathing out a bunch of, I guess I shouldn't say breathing out, they're respiring a bunch of oxygen at this time as well. So that's when we would see high oxygen. And then finally in the fall, like right now, with all the leaves flopping on the ground and dying, they're respiring that carbon dioxide back into the atmosphere because they're decomposing. So we're going to have a higher amount of carbon dioxide in our atmosphere in the fall because they're all dropping and they're all respiring carbon dioxide. That is the annual cyclical pattern that we're seeing here. We're going to talk more about this. I wanted to bring this graph in now because it's a relatively simple graph to read, but it's also very famous and it's definitely going to be shown more than once in this class, especially when we talk about climate change and human factors regarding climate change. Okay, let's talk homework 1. This is really weird. Usually this is when I'm like, do they have any questions? But you can't answer that. Let's talk homework 1. So this is the document on your Canvas. I'll just go there right now. Because I know there's going to be questions regarding this homework assignment. It's the first time we've written it, so please let me know if you have any questions, if there's anything that's not clear. But essentially, I'm about to read you the instructions from these. You can either read it in the document form or the PDF form. I don't care. They're the same thing. So your homework 1 is you're going to use ChatGPT for the scientific method. You're going to use ChatGPT to help answer a question about an observation that you've made. You're going to make an observation. I do not care what this observation is, as long as it's related in some capacity to the environment, because we're in an environmental science class. Yeah, pertaining to environmental science that people have access to, like people are thinking about, not just you. And it has to be actionable. It cannot be a property. So like the property being, you can't make the observation the grass is green. That's just going to be too hard to answer. So it has to be actionable. Like the high tide occurs every 12 hours, or the glaciers melt every summer. Those are actionable. Those things are happening, right? And if you're not sure if the question or observation that you have is appropriate, send me an email. Happy to answer that. But I want it to be actionable. So then you're going to ask a question about the observation that you've made, like, why does high tide occur every 12 hours? Or why are the glaciers melting every summer? I think that's actually what I talk about in the example that I give. You're going to hypothesize an answer to this question. So think about things you already know, like high tide occurs every 12 hours because of the moon. Okay, that's fine. I'm happy with that hypothesis. And then why do glaciers melt every summer? Oh, maybe because the summer is the hottest point in the year, and so the glaciers are melting because it's super hot. And I don't care if you're wrong. That's the whole point about science is we're wrong all the time. You just have to use logic to help kind of hypothesize something to your question. I need you to think, oh, well, I don't want you to say the glaciers are melting in the summer because the trees are at their fullest. Like that doesn't make any sense. There's no connection there, right? But if you say, oh, it's the hottest point in the summer, like there's a connection there. Love that. That's what I'm looking for. And then you're going to set up an experiment. How would you maybe test this hypothesis? We're not going to test these hypotheses because we can't. We're just doing a basic assignment here. But what's something that you could do to help set up or to help answer that question? So for instance, for why do glaciers melt every summer, we would set up like maybe we'd have satellite imagery to look at the glaciers to see when there's the most glacier, when there's the least glacier. We might set up thermometers and look at temperature data. We might look at at like 5 different glaciers to see what's happening. So just think about how you would set up an experiment maybe and write some steps, okay? And then you're gonna go to ChatGPT. So, hi. This is where we would take the data and assess and interpret what the data meant. Have I made it this far? Yeah. Because we're not going to actively test this theory by doing a real experiment. We're going to input this question in ChatGPT. ChatGPT. So we're going to say, why do glaciers melt every summer? Well. And then ChatGPT is going to spit this out. And what I want you to do is copy and paste this answer. So you're going to copy and paste all of this into a Word doc and make it known this is what ChatGPT said. I have this in the example document as well. And then what I want you to do is you're going to find an answer within this answer. I want you to read the answer and then find something within this answer to then ask another question. So for example, this says, okay, precipitation. Rainfall can also contribute to melting, especially if it falls on already warm ice. Then you could come up with whatever, but what I want you to ask is something regarding something in this question. So we'll say, how much rain affects glacial, melt? Oh, and then it's going to spit out another answer. And the reason, I think you do this 5 times. I think I have you do this 5 times. So you're going to look at this again. Find another question to ask the question, have it spit something out. Do it again. And the reason I want you to do that is because I want you to get in the habit of reading these answers, not just copying and pasting, but reading the answers, understanding the answers, and then maybe being like, oh, that's a great answer, but I don't fully understand this part. What is ChatGPT saying about surface conditions? I don't understand. And so I want you to ask that question. Copy and paste the entire conversation that you've just had into a Word doc, the Word doc that you've already written your observation, your question, your hypothesis, because I want you to write all of this stuff down and then copy and paste your conversation with ChatGPT. And once you're done with 5 questions, you're going to conclude. So the last thing you're going to do is write 2 or 3 sentences summing up your ChatGPT answers. Listen, I get it. You've already got ChatGPT open. Why not utilize that? So what you can do is, let me go back to ChatGPT. And I did this, and I kind of love this. Summarize the last 2 answers. You'd say 5, right? Look at that. Spits out a summary. Please rewrite this in your own words. But it spits out a really nice summary. And like, obviously there are some, Henry, I'm trying to talk, I know. Obviously, there are some things you can't change. Like when it says glaciers are melting every summer, you can't change temperatures, increased solar radiation, climate change. There are some words that you're going to use that are the same here, but think about how you can rewrite this to benefit you so that it's not the exact same. And then you're going to write that. Where am I going? And ChatGPT will give you a nice summary. However, the whole point of this assignment, now that we're at the end, so we've done the entire scientific method step by step. But what I want you to note is ChatGPT a valid and reasonable way to answer scientific queries? And maybe it is, but maybe depending on the question that you ask, it's not the best source. So what you're going to do, and again, you can use ChatGPT to do this. And I think that ChatGPT is such a great source for this because writing a thesis was a struggle bus when it came to finding sources to write about. So what I want you to do is you're going to find 3 other primary sources. And if you need help understanding that, please remember that you have How to Write a College Paper. And this talks about how primary source is the very first source when collecting data. So it's the raw materials of history. It's the original documents, diaries, correspondence, ship's logs, biographies, autobiographies. But it can also be manuscripts or interviews, speeches, oral histories, master's thesis. I wrote that because I just finished mine. So any sort of scientific journal article would be a primary source. I don't want you to find secondary sources. And these are essentially Wikipedia articles, news articles. News articles are great, but news articles are usually the secondary source in communicating material to the public. However, both of these examples that I've given you have primary sources located at the bottom, or a news article will say, I spoke to this author regarding this article. Here's what he had to say. And so that article will be listed. Click on that article. With Wikipedia, it's the same. Let's do Wikipedia. Oopsie. Mount Baker. So here's the Mount Baker Wikipedia page. There's so much here that's really great, and some of that is true. Fun fact, this is not true. That's a lie. I mean, it is also known as Comacultion or Coltion, but it says that it was given those names based on Lummi and Nooksack native languages, and that is a lie. We can talk about that later too. It doesn't matter. So it has all this really cool information, and I love Wikipedia for this, but none of this is considered primary source. But if you go all the way to the bottom here, these are considered primary sources, and I am absolutely okay with you clicking on one. It'll take you to that primary source. And this is what you cite. You do not cite Wikipedia. If I see Wikipedia in a written source and you say, oh, I got this information from Wikipedia, you're getting docked points. That is so important. But you can use all of that super, super important information at the bottom of Wikipedia. Okay. Oops. Where am I going back? Go back here. Yes. So what I want you to do is validate the information that ChatGPT gave you by finding 3 primary sources that either back up the information that ChatGPT said. You say, oh, ChatGPT said that rain can affect glacial melt by direct melt contribution. And Geological Society of America wrote this article saying that rain can directly increase the amount of water, leading to faster melting. Here's the source that I have. And you're going to find 3 things that either back it up, or you say, you know, ChatGPT said that warm rain does this, but actually this scientific source said that cooler rain can accelerate melting even more. It doesn't. That's a lie. But I want you to find sources that either back it up or say something that does not back up what ChatGPT says, because that's what I want you to get out of this. I'm very excited about this assignment. Where am I going? So that's what I want. And then you're going to cite those sources using the same, I'm all over the place, I'm sorry. The same How to Write a College Level Research Paper, how to cite a source as a reference in your paper. Please, for the love of God, just use EasyBib. I love me some EasyBib. I used EasyBib for my entire master's thesis, you guys. I did have to move some stuff around, but type in your source to EasyBib, type in the link or type in the name of the article and it will pop up the site or the source. That's perfect. That's all I want, okay? And it'll look something like this. This is my bibliography. And when you well, we can talk citation later, but that's all I want. I want you to cite your sources appropriately, and I want them to be good sources. I will be looking at your bibliography uh, to see that it's not Wikipedia or ChatGPT. You cannot cite ChatGPT. Oh, but the point I was trying to make is, what are some primary sources for glacial melt? Boo, 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 doo. Uh-oh, that was a terrible way to primary reference sources for glacial melt. You might have to dig around a little bit. You might have to type out a few things. Here we go. Okay, so here they're giving you some really good primary sources. I'm going to look up Geological Survey. Here are some articles in journals to look up. And they might not give you specific articles. Obviously, this guy didn't. But you might go into, you can type up nature in Google. Use Google too. You don't have to use ChatGPT. So do what you got to do to find some primary sources. And I will be looking at the sources to make sure you got the right one. So that's your homework one. Sorry this was a long video. Again, you can watch it 2 times speed. I don't feel that bad. Let me know if there's something still unclear about the homework, or if you have a question about whether or not your observation is appropriate for this assignment, shoot me an email. Happy to answer. Otherwise, that's your module for this week. Is just understanding the scientific method. You will be making a discussion post about this homework assignment because I want you to share with your classmates what question you asked and whether or not you thought ChatGPT was reliable. And you know what? It's okay if you say, yeah, for this particular question, it had really good answers. It gave really good responses based on the sources, the outside sources that I found that validated this material. That's okay. I didn't write it so you'd say, no, it's not good. I'll never use ChatGPT. That's not what this assignment is about. It's about understanding how to use ChatGPT in the case of a scientific query and how to use it appropriately. That's what I want you to get out of that, because I think that embracing ChatGPT and AI as a form of understanding scientific research is super important. I think it's going to be great. That's our move to the future anyways, is as we get more information online and it starts to generate these answers, how do we use that? How do we utilize it? But there's also a lot of information that is not correct going onto the internet now, as I'm sure you all know. So how do we validate the material that ChatGPT spits back out? So that's your assignment. I'm really stoked about it. Talk about it in the discussion after you introduce yourselves. It should be a pretty chill module. And please reach out and say hi to me, introduce yourself. I'd love to get to know you all. Now you know me and Henry very well, so sorry about that. And I will see you the rest of this term. I'll send out some announcements. Turn on your announcement notifications, please. Okay, bye.